All right, here we go, friction basics. So we're basically just going to do a real fast review of friction, just kind of refresh your memory about how friction works. If you want a more detailed explanation of all this stuff, I definitely would encourage you to go back and watch the honors videos, okay? So here we go, friction basics. So remember, friction is one of the forces applied by a surface that an object is in contact with, right? We've already talked about normal force, which is a force that is perpendicular to the surface that the object is in contact with. Friction is parallel to the surface at the point of contact, right? And friction will do one of two things. It'll either try to prevent two objects from sliding, in which case it is called static friction. I paused this video. I actually don't like this. It says it works against the attempted motion of the object sliding across the surface. It works against the attempted sliding between two surfaces is probably a better way to say that. So there you go. All right, if the object is already sliding, then we delve into a second type of friction, which is down here in red, kinetic friction. Okay? So two types of friction. Static friction tries to prevent the two objects from sliding across each other. If it is already sliding, then we call it kinetic friction. Okay? So static friction, here's what you need to know. First of all, static friction only occurs if the object is not sliding, but it would slide if there wasn't static friction. Okay? It always acts in the opposite direction. The object would slide. If there's no friction, it will be parallel to the surface. All right? So examples, Roy trying to slide a box across the table but not pushing hard enough, static friction prevents the motion. A car speeding up, friction is actually what causes the object to go, right? Because if there's no friction, the tires are going to slide across the road. But static friction prevents the tires from sliding, the tires grip the road, and static friction pushes the car forward. So that's a perfect example where static friction isn't actually resisting motion, it's actually causing motion, right? Okay, this is the big thing. And I remember this being confusing for some of you last year. Remember, static friction is lazy. That means it's going to exert as little force as possible in order to prevent the two objects from sliding across each other, okay? Yeah, so this is kind of illustrating that idea that in the case of walking or driving, static friction doesn't necessarily make the net force zero. Last year it frequently did. This year that will not always be the case. Okay, so static friction. So when two objects rub together, there's a maximum amount of force that static friction can exert. How much force static friction can exert depends on what two surfaces are rubbing together. Remember, that determines your coefficient of friction. Remember, Greek letter mu is the coefficient, S for static. Okay. Two surfaces that are smoother are going to have a lower coefficient of friction. Less slidey, should probably say more slidey, right? All right, so two surfaces that are smoother or more slidey are going to have a lower coefficient of friction, and if it's rougher or more coarse, you'll have a higher coefficient of friction, okay? So here's a few examples of some different coefficients of friction, all right? The force of friction also depends on how tightly the two objects are being pressed together, which is determined by your normal force, all right? Ultimately, here you go. Your force of static friction is always less than whatever your maximum value is. And to calculate that maximum value, you multiply the coefficient of static friction by the normal force, okay? So usually what we have done in the past is you calculate this to figure out how much force static friction can exert, and then you just know that friction is lazy and it'll always exert some amount less than whatever the max is, okay? Just a quick note about notation. A lot of books just use F for the force of friction instead of F with a subscript F. And a lot of books use N instead of Fn for the normal force. I try really, really hard to indicate every force in my class with an F, and then the subscript describes where the force comes from. But just know when you get to wherever you're going for college, they might use slightly different notation. All right. So Here we go. It says, suppose the coefficient of static friction between a rubber tire and dry asphalt is 0.8. What's the maximum acceleration a car could possibly have? All right, well, let's draw ourselves a car. So here's the car. Okay, so the car has a mass of m, right? So automatically I know that there is, whoa, it's not what I wanted to do. Try that again. I know that there is the force of gravity, which is negative mg, right? The car is presumably sitting on the ground, and thus there is a normal force big enough to cancel out the force of gravity, so that's going to be positive mg, all right? And then what happens is the car accelerates, right? How does that happen? Well, the idea is when you press the gas pedal, that makes the wheels spin, right? So the wheels are trying to slide backwards across the ground. Static friction prevents that and pushes forwards. All right, so if we want to find the maximum acceleration, we want to maximize the force pushing the car forwards. Okay, and so, oops, not what I need to do. So the force of static friction maximum is our coefficient of static friction times our normal force, which is 0.8, and our normal force is mg. All right, and so now we just do net force equals net force, right? So our net force, according to Newton's second law, is mass times acceleration. According to the sum of our forces, these forces are going to cancel, so our net force is just the static friction, which is 0.8 mg. Let's see, the m's cancel, and so the maximum acceleration we can get is 0.8 times g. So 0.8 times 9.8, which is 7.84 meters per second squared. Okay. All right. Kinetic friction. So kinetic friction I always find to be a little bit easier. First of all, as soon as the object is sliding, you know there's kinetic friction. The nice thing about kinetic friction is that the value, the amount of force that kinetic friction exerts is fixed, all right? So remember, kinetic friction always opposes motion. This was the big thing people got mixed up on last year. Kinetic friction opposes motion, not force. All right, so for example, we'll go back to the infamous Superman stopping the bus example. So look, if you've got, oh God, try that again. So giant monster has just thrown a bus. The bus is going this way. Superman's going to try to stop it, right? All right, so here's the force of Superman. Which way is friction going to act? Well, friction doesn't want the bus to slide either, right? So friction acts this way. Okay, friction opposes the motion. All right. So let's see. Kinetic friction only occurs if it's sliding. Kinetic friction works against the box sliding. A car that's spinning its wheels when it's speeding up, that's going to be kinetic friction because the tires are already sliding. This is the point that I was just trying to emphasize. Friction always acts in the opposite direction the object is sliding, regardless of what other forces are acting on it. All right, the direction that friction acts in static friction, the direction kinetic friction acts in has nothing to do with the other forces on it. It has only to do with the direction the object is sliding. Okay. Similar to static friction, the force of kinetic friction depends on this coefficient of friction, which we call mu k. That depends on, kind of the roughness of the surfaces and the normal force, okay? So once again, there's your force of kinetic friction. The coefficient of kinetic friction times the normal force. All right? So probably best to dive in. We're just going to do a couple examples here. So let's see. We already did this one. Here we go. So this one, honestly, is one you probably could have done last year. So we got a 20-kilogram box that's sliding. Let's do this. And okay, so we got a 20-kilogram box sliding at 8 meters a second across the ice toward a cliff that is 10 meters away. So let's draw it. Floor, 20 kilograms, sliding at 8 meters a second. Remember, this is not a force, so I didn't draw it as such. It's sliding towards a cliff that's 10 meters away. Coefficients of static and kinetic friction are 0.3 and 0.2. Coefficient of static friction is 0.3. Coefficient of kinetic friction is 0.2. Let's see. In part A, Roy pushes the box back. Here, let's do this. So we're making a free body diagram, right? So last year, I really encouraged you guys to kind of follow the same steps, right? So the steps were, start with your force of gravity, right? 20 times 9.8. There's no other vertical forces. We'll find out here in a minute after we finish reading this thing. So that's going to be 196, all right? So then you do your given forces. I probably should have held off on this. So it says Roy pushes the box back with a force of 300 newtons. So here's my force of Roy, negative 300 newtons. Sally pushes the box forward with only 250 newtons. Make a free body diagram and describe what the box will do. Okay, well, my free body diagram is started, but I need to do something with this friction, right? So let's move these guys over. All right, so I guess at this point, I might as well take a quick second and do this. Let's find our force of static friction maximum by doing coefficient of friction times normal force. All right, so if you do that, you get 58.8 newtons. And similarly, we can find our force of kinetic friction, which is the coefficient times the normal force. And so that gives you 39.2 newtons. All right, now, because the box is already sliding, that means I've got to use the kinetic friction. All right, so put that onto your drawing. FFK, it's opposing the motion, right? So negative 39.2 newtons. I just glossed over a thing that was super important. All right, here's what I just did not emphasize that I wish I had emphasized. The box is moving to the right. As a result, friction is acting to the left automatically. Last year, I remember there were a lot of people who would look at a problem like this and they would think, oh, Roy has more force than Sally, so friction's going to help Sally. And that's not right. Remember, force of friction, force of kinetic friction, rather, has nothing to do with the other forces, but only the direction of motion. Box is moving right, friction goes left. Okay? All right, cool. So that is that. So part A, we can finish solving this. Net force equals net force. So mass times acceleration is the force of Sally plus the force of Roy plus the force of kinetic friction. So 20A equals 250 minus 300 minus 39.2. Okay, and solve for A, and you end up getting negative 4.46 meters per second squared. So the box is going to slow down and eventually stop. Part B, how far will the box slide before stopping, or will it fall off the cliff? Let's see. So let's see. We know this. We know our initial velocity is 8 meters a second. Our goal is we want the box to stop, and we want our displacement. So I think we can just use one of the kinematics equations. So plug in your numbers and solve this, and we end up getting 7.2 meters, which means that the box is safe. All right, so the box is going to stop before it goes off of the cliff, right? Now, let's do part C. Part C says, suppose Roy and Sally continue pushing after the box stops. All right, so let's go back to our drawing over here. Here's our box. Part C. So we've got our force of gravity. It's still negative 39.2. No, it isn't. Sorry. It's negative 196 newtons. We've got our normal force, positive 196 newtons. Roy and Sally are still pushing. Here's my force of Sally, 250 newtons. Force of Roy, negative 300 newtons. Right now the box is stopped. So if there was no friction, the box would move to the left, right? Because Roy is winning. Okay, but remember, static friction. The box is at rest, so we don't know. We're not necessarily at kinetic, right? Okay, the box is at rest. So now I want to be thinking about my static friction, right? So remember, static friction wants to prevent the box from moving. So can it? Well, in order to prevent the box from moving to the left, we need more force to the right. How much more force? Well, we've got 300 to the left, 250 to the right, another 50 to the right will make my net force equal to 0, and so the box will not move after the box stops. In other words, it'll stay at rest. Okay? So this is a problem you theoretically should have been able to have done this last year. All right, let's ramp this up one difficulty level. All right, so it says Roy's got a new job. He works at the museum. Unfortunately, having recently run out of nails, the museum, is now paying people to hold paintings to the wall. All right, the coefficients of friction between the wall and Roy's 5-kilogram painting are 0.4 and 0.3. Remember, your bigger one is always the static one. All right, so my coefficient of static friction is 0.3. No, I try it again. The bigger one is static, and the smaller one, why are you doing that to me? Stupid smartboard. All right, so there's that. All right, so let's make a drawing. So here's the wall, here's the painting. It's 5 kilograms, right? So it says Roy pushes the painting horizontally. So automatically I can put in my force of gravity, right? That's just going to be 5 times 9.8, so negative 49 newtons. All right, Roy is going to push the painting horizontally with enough force to prevent it from moving. But in order to prevent the painting from moving, we need some sort of upwards force, right? But what is that upwards force? Well, the idea is because Roy is pushing the box to the right, he's creating sort of pressure between the picture and the wall. He's creating a, well, maybe we should ask this. Roy's pushing this way, why doesn't the box move that way? Oh, there's a normal force, right? These two forces need to be big enough to cancel each other out, right? Or specifically, the normal force is big enough to cancel out Roy's force. And now that we've got a normal force, we can have some friction. If we don't want it to slide, then this is static friction. If we want to minimize Roy's force, then we should maximize static friction, right? So, to maximize that, well, the idea is we want our net force vertically to be 0, right? So that means that this has got to be 49 newtons, right? Okay, well, oh, and we know our coefficient, right? So force of friction static max is coefficient of static friction times normal force. So we need at least 49 newtons of static friction. Our coefficient of friction is 0.4, produced with a normal force of something. Divide both sides by 0.4, and you discover that your normal force is not written on this piece of paper that I'm looking at, but it is on this one. So you get 122.5 newtons. That means that Roy's force must also be 122.5 newtons, right? Okay, so that's part A. All right. Part B says just before quitting time, he gets tired and he only exerts half as much force. All right, well, so let's make a new drawing. So here we go. Here's our thing. It's still 5 kilograms. Gravity's still going to pull it down with negative 49 newtons. Now, Roy's force is half as much as it was before. So what is that, 61.25? All right. Well, the box isn't going to move to the right, so there must be a normal force pushing back with a force of negative 61.25 newtons. And that's producing some friction. Let's see how much friction there is. Well, let's see. Clean up my drawing over here. Let's get rid of this. I need some space. All right, so for my new problem, for part B, let's find our force of static friction max. We already know it's not going to be enough, right? But just to make a point, that's coefficient of static friction times normal force. So we've still got the same sort of roughness between the picture and the wall, but our normal force is only 61.25 newtons. So when you multiply this, it only gives you 24.5 newtons. And since gravity is 49 newtons, that's not going to be enough. All right? So we got to go to kinetic friction, right? In other words, the picture is going to move, right? So force of friction kinetic is our coefficient of kinetic friction times our normal force. So that's 0.3 times 61.25 gives you what, 18 point something, 675, 375, 18.375. All right, so there's my kinetic friction. This becomes kinetic. And now we can do net force equals net force. So mass times acceleration is force of gravity plus force of kinetic friction. I guess technically this is all in the vertical direction, right? Because horizontally everything cancels. All right, so we're going to get 5a equals negative 49 plus 18.375. Solidify it, and your acceleration turns out to be negative 6.125 meters per second squared. All right. All right, one last example, if I remember right. Oh, no, that was it. Cool. All right, I was thinking, must have been thinking about an example from the next section. So there you go. Super quick review of friction.